I'm not going to start from the basics because it's all there. We'll take one or two lectures at a time and summarize them and then let you start the discussion. Once the discussion gets started, I will come in and explain to you if you have something which you are not able to understand, or if I want to say something new which is not in the NPTEL lecture, then also I will intervene. So without the discussion part, this course will lose its value. So all of you I request to come prepared every time, except today, of course, you don't know what we are going to teach. Come prepared with the courses from NPTEL. You know how to do that. You go to the YouTube, or if you have the CDs already, you play them and watch them before coming to the class. I will request you to interrupt me whenever you have a question or a doubt. Don't wait for the lecture to be over, because somebody may have a doubt and the other person also may have the same doubt. If you ask then and there, it will be better so that I can clarify it for everybody. At the end, of course, everybody will be in a hurry to leave, and of course you can always send me an email explaining your doubt, and I can also reply in the next class. But it will be better if you ask the questions immediately, then and there. So I will show you the contents of the course, and that will be followed more or less depending on the progress of this course. Yes, can you put that contents? Course content. You can see on the screen. Firstly, this is the list of lectures I'm going to give. All related to NPTEL except a few new courses, courses in which I will introduce new material. This you are able to see. These are the summary first two lectures today. I don't know how far it is going to go. We will see. Then I am going to introduce two more material which is not there. Lecture content. Right. You go to NPTEL website, IIT Madras. There is a flashing web link called online course. You click that and you will get this. And then this will give you the description of the entire course. But what you can see is most significantly assignments and problems. Because the earlier NPTEL program, we did not have assignments or problems. So since this is taken as a course by all of you, I will give you a lot of assignments and homework problems. You are supposed to solve them. We will also, first I will send you the problems, and then after some time we will also give you the solutions. The mentors in each center will monitor your homework and assignment problems, collect them and correct them. So that aspect is left to them. So, but we will keep giving you the lectures. Similarly, there will be exams which will be prepared by us and sent to your mentors. The mentors will administrate those exams to you. You will do those lectures, and then you do these test problems, and then you will be able to understand fully this course content. Now I have been talking for about 10 minutes, taken the digital course, because it is one of the basic courses taught in any engineering college, especially for ECE, EEE, instrumentation engineering and all that. So it is not new, material is not new. But the difference between what you have learned and what we are teaching is problems. And that way you should have complete knowledge of this course at the end of the program. Because when you read from a book, there are certain things which you don't understand. So you proceed to the next chapter. But when we do it, we make sure you all understand everything. That is the plan. So now let us see what is a digital system. You can go through the whole thing. What is a digital system? Yeah, that is the course material. Run it through the, okay, approximately 2 lectures a week unless there's a holiday. Come down, man, fully. What is this? Oh, that is the course. Leave it, leave it. I don't want to waste time on this. Okay, so we will start with the definition today. What is a digital system? Why do we do this digital? Today computers are everywhere. All the processing of signals, processing of data, everything is done in computers. These computers basically do digital signal processing. They process numbers which are digital, signals which are digitized, and this is easy because we can write programs and we can get to do what we want to do. But in nature, everything happens analog. For example, take the ECG signal. It's an analog signal, varies with approximately 1 hertz per minute. And there are some signals which are analog. For example, the speech that I give today is an analog because the output of the microphone is analog. You have to hear it also from a speaker which is also analog. But how do I make this? I convert this signal to digital and then do the processing, whatever processing is required, amplify, cut the unnecessary components, remove the noise, whatever is that you want to do, excuse me, and then bring it back to digital form. This is only a couple of examples. Video signal also. Nowadays, of course, they are going for digital TV, but until now it is analog TV. Signal is analog from camera, and it is digitized and then processed. All these extra things that we put, multi-screen, for example, today. A lot of these things happen in digital domain, and then finally it is converted into analog in your monitors. Like that, there are so many examples I can give. Seismic signal. Seismic is earthquake activity. That is also analog signal. So we need to first step in any digital course is to understand a digital signal. What is a digital signal and how does it differ from a normal signal which are used to, which is called analog signal. So I will write down on the board. See, I have a signal. What is a signal? Signal is something which varies with time. And it has an amplitude. An amplitude versus time. Now this amplitude can vary from a minimum value which is defined, can be 0, need not be 0, it can be negative, doesn't matter. Similarly, there is a maximum amplitude. Between these two limits, the signal can take any value. This is called analog signal. An analog signal can take any value within the limits defined as a function of time. Now, it is difficult to process this because when you, first of all, you have to pick up properly the signal, make sure there is no noise overriding on this, and then finally when you process and present it to the the destination, we don't know whether this is the original signal, was it corrupted with noise, was it reduced because of some drops, we don't know all that. So what we do is, all of you know this, I'm sure, we discretize this. This is called discrete time signal. In a discrete time signal, it goes between minimum and maximum, there is no change in that amplitude. And time is also given, same as previously, but we only sample the signal at limited intervals, at fixed intervals. How frequently you should sample it depends on this frequency signal in the sampling theorem. All of you may be familiar, or if you are not familiar, it will be taught to you later on. So we have to make it sufficiently close so that we will be able to reproduce it without any problem, without losing the contents. So that is called, the same signal I will take, but I will not transmit the whole signal, I will do it at fixed intervals of time. How frequently depends on the frequency of the signal and on the communication principle of sampling theorem. I am not going to get into the sampling theorem, you know that. If you don't know that, it will be taught very immediately after one or two courses. This is an early course again in your digital, in your syllabus, engineering syllabus. That means if you do it properly at a reasonable rate, with the discretized time being a small amount, you will be able to reproduce it without any loss of information. This is called discrete time signal. So at least we know that between 2 points we are discretizing or sampling, we are assuming the signal doesn't vary. Even though it varies, we will assume that to be same as this. For example, at this point, until the next sampling interval, we will say this is the signal. At this point, we will say this signal. So this sort of eliminates the need for actually transmitting it every instant of time. Every instant, I don't know whether it's seconds, minutes, microseconds, nanoseconds, don't know. At least we know now, within fixed limits, the signal will not change. Within given limits of time, signal will not change. We will assume that. And that should be, if that is true, we have to do it as fast as possible. Then this is also not good, because when you transmit this, this sample value has to go to the receiving side. It may be corrupted by some noise, or it may be corrupted because there may be a drop in the voltage. So what you do is, we do a digital signal, which is third possibility.
Digitally coupling the load.
Digital signal, again we have minimum and maximum values and the amplitude. The time. But now we will assume digitally the value of minimum maximum, not any value it cannot take. It can only take a predefined number of values. For example, This may be a value. This may be a value. I divide this interval equally. So this signal variation, I will put it, okay, here, this signal will be this. Next point, it may be this. And then it may be this, because it is jumping steeply. And then it may come down, somewhere here. It will come down. The amplitude will change to the lower value. Then it go higher. Then it goes lower. It's all within the defined values. Only certain values are allowed in the amplitude. These amplitude values are defined by your requirement for accuracy. If you want very, very accurate reproduction, you should have many samples, many levels of values between minimum and maximum, because it can only the signal can only take the given values defined along the amplitude. You cannot get a value in between. It will be approximated to one nearest. So if we get, for example, this value for the discretized signal, discrete time signal, and if you don't find an equivalent value, you will take the nearest this value. Nearest is this at this time. But how many steps do you divide? That depends on the accuracy with which you want to reproduce. I can have only 4 levels. That means this will be one level, somewhere here another level. Between, for example, there are only 4 levels. Minimum is 0, maximum is 5, let us assume. There's no compulsion you should have these values. I'm just giving an example, arbitrarily. So now, this is divided into 4. Halfway, quarter way, 3/4 way. So all these points that you sample have to fall in one of these. So I can have either this value, or this value, or this value, or this value, nothing else. What is the problem with this? Because accuracy is lost. I want to reproduce the signal. That's what we started. We started trying to reproduce the signal. But the signal, too much of a burden to track this signal every instant of time, because instant of time is not defined. It can be microsecond, second, depending on the variation. It is supposing you take the temperature of the day, you don't have to do it very, very frequently. Once in an hour, even that is not required. Maybe once in 2 hours, once in 3 hours. Take the temperature. That is enough. Or if you want to do a seismic activity, there is earthquake activity. It doesn't change much. Once in a while, maybe once in every day. On the other hand, you do a video signal. Video signal has very high frequency. You have to do it very, very fast. So that is the first definition. You discretize the signal by allotting different intervals of time based on the variations available, variations at which you want to reproduce. Then the discretized time also has a problem of amplitude, because I want to try to send these values, discretized values, over the transmission line or whatever. It is very difficult to reproduce because it may be corrupted. Even in a digital signal process, there will be corruption because of certain problem. There may be noise overriding, or there may be a voltage drop. So we want to avoid that also. We want to go for, given the amplitudes at fixed intervals, time at fixed intervals. Time interval depend on the frequency of the signal. original signal. If it is very large frequency, you have to do it very frequently, sampling. Because the Shannon's sampling theorem says the frequency and depends, the sampling frequency depends on the frequency of the input signal. I am not going to get into the sampling theorem definition. If you may know, if you don't know, you will please read it. If you don't want to read it now, you can read it later. You will be exposed to this by communication professors. Okay, that is the time interval. Amplitude interval depends on how much accuracy. I don't want this. For temperature, what is the accuracy I want? I want 1 degree accuracy. That's enough. If I do something else, I want more accuracy. So number of levels at which you divide the amplitude depends on the accuracy with which I want to work. So finally, a digital signal is discrete in both amplitude and time. That means basically I can represent them by numbers.
Amplitude time, no? But data প্রথমে দেখালো সেটা কি ছিল? ওটা ছিল discrete only time. Amplitude constant.
Now we come to the real use. When I can represent something by numbers, I can put it in a computer, store it. I can put it in a computer and process it and get the result. So it is easy once you have numbers. Also, when you put a series of numbers in a computer, very rarely the value gets changed. The values remain. Whereas when you say analog signal, first of all you cannot store it. How do you store it? You need a capacitor. But then how do you know whether the capacitor is not leaked? When you try to take it out after some time, the value will be different. How much was the original value, you don't know. If you know the original value, there is no point in doing any processing at all. But since you don't know the original value, we'll have to depend on the value stored, and that value may be different after some time because the value has dropped. Capacitance has leaked. Now digital, there is a problem. It is not that always the signal will be reproduced accurately, but the accuracy with which you can reproduce a digital signal is much better than accuracy with which you can replace the store and retrieve an analog signal. That is the point here. So once you have a numbers to represent something, then the best thing is a computer. Computer is a big word. We don't need computer every time. A microprocessor sometimes will do. Digital signal processor will do. Or some simple combination of gates and counters will do. All these work on digital principles where signals are discretized and the time is discretized. That is the concept of analog, discrete time and digital signals. So why are we choosing this digital signal? As I again said, the values do not change that much. Occasionally yes, but generally not. And we can replace, we can sample them at the frequency at which it is required, not more frequently than that. That is the idea. Now, this advent of computers has helped a lot. It is not that this concept was not known earlier. It was there, but then there was not proper mechanism to store the values. And even if you store the values, to process them, we didn't have a proper mechanism. Once the computers, as I said, when I say computers, it is not the desktop computers. It can be any device with a CPU, memory, input, output units. It's a computer. It can be as simple as even your cell phone is a computer because there's an input you can talk to, there's a microphone, output is a speaker, there is a memory where you store your addresses, and a process. It retrieves when you want to call a number, you go to the address book and get the number, or you want to store your number, you go to the address book and store it. So that way is the simplest example of a computer, or a microprocessor, or a digital signal processor. All of these things are. Now I can use now, without going to the theory anymore, of signals, analog, digital, discretized, I can now go into the numbers and how these numbers are represented, how you process it. Now, I said there are only fixed levels. I need to represent the numbers by these levels. So whatever value I get for the signal, I should be able to, for example, this one there are only 4 values. So 4 values will be, if I have only 2 values, one value I will call it 0, the other value I will call it 1. So 0 and 1. 0 does not mean it is 0 volts, 1 does not mean it is 1 volt, it is only symbol. But generally 0 is 0 volts, 1 is some value that you are using like 5 volts or 3.3 volts or whatever, 1.8 volts, 0.8 volts, whatever is the power supply we are using. That is the 0 and 1. So let us say it is 0 to 5 volts because earlier logics, so-called TTL and even the basic CMOS circuits worked with 2 levels, 0 and 5 volts. So this is a signal present, signal absent, which is represented by 0 volts, and this is signal present, represented by 5 volts. So I have 2 levels, no problem. When I want to say signal is present, I will put 5 volts on the input side of the microprocessor or computer, whatever I want to work with. And when the signal is absent, I will put a 0 volts. But that is not enough. As I said, the accuracy is not enough. Every time I can only, for example, temperature, you want to measure from somewhere from 0 degrees or not 0, maybe in India, 10 degrees to about 35-40 degrees in summer. I can have only, it is either low temperature or cold or high temperature or hot. In between I want to know now, for example, in December, January, temperature may be somewhere like 20 degrees or even less in some places. In Chennai where we live, it is about 20 degrees. Now, I should be able to represent 20. So 0 and 5 only means I cannot do that. So I need more values. So let us say I divide this temperature scale by into 8. So 8 values of temperature. 8 values can be 0 degrees, which is not generally done in India. Nobody, in Kashmir, yes, it freezes, but generally not. In our part of the country, 0 is never heard of. We only read in paper about cold wave in northern India. And we'll say 8 values from 0 to 40. That's it. 0 divided by 8, 0, 5, 10, 15, 20, 25, 30, 35. 8 values are gone actually. 0 is 0 degrees, 0, 1, 2, no, this is 1, 2, 3, 4, 5, 6, 7, 8. So I cannot have both 0 and 40. Minimum of 40, one of them I can have. So I can either want to start with 5 and go up to 40 or start with 0 and go up to 35. That is okay. Because why I am saying this, I can also put 0 and 40. Now how many times, if you divide a signal by 8, you want to represent everything in a binary number. In computers, everything works with binary. Computers also work with binary. Everything is binary. Binary means your program is binary. You write program, C language program or whatever program you write, but that has to be converted into binary before the computer understands it. You don't do it. That's an interface. You give a program, you give data, whatever way you want, but before it actually reaches the CPU of the computer, it is binarized. So, how many values are required for 8 values? How many bits are required? 8 bits. 3 bits. 3 bits means 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 110, 111. So 0 to 35 I can divide into 8 parts and represent by 3 bits of a binary. But I can also have the fourth, 40. In that case I need one more bit. So generally I want to represent by 3 bits, it becomes 4 bit. That means I'll have to put 4 bits everywhere. Depends on you. If you want to do it that way. But generally you limit the number of bits in your computer. Number of bits are divided by the accuracy I told you. Same time you don't have to overly have a number of bits, more than what is required. What is the accuracy required? Do it. So this is how the digital system works. So once you have a number, whether it is input to the computer, input from memory, program memory, data memory, whatever you do, we are now in high level language. Earlier it was assembly language. One has to write a code. Before that, it was a binary. You write the program in binary. All those days are gone now. We don't do it. We write the program in the language, C language, Verilog, VHDL, whatever. But then that gets converted automatically. Data gets converted automatically. Everything gets converted to binary. So we like to define how many bits are required for any particular signal. In this case, I define 3 bits, so I can only have 8 values. So when I divide 40 by 8, it is 8 values, 40 by 5, because 5 is the accuracy I want. There are 8, but then 0 and 40 both are included, it becomes 9. We can't have that. So we can either not have 0 degrees. We'll say 5 is 0, 0, 0, 10 is 0, 1, 0, etc. Then 35 will be 1, 1, 0, 40 will be 1, 1, 1. So if you don't have 0, or if you want to have 0, you cannot have 40. You have to make up your mind on that. This is how we define a digital signal, and that is how we do this. Now why do we do this, as I said? See, digital signals are easy to work with. Digital signals are easy to work with. Why is it easy to work with? First of all, you can convert it very easily, and then the processing is done by computer or DSP or whatever. All you have to do is write a program. When you try to build an analog circuit, you have to build the circuit properly. You have to make sure it doesn't pick up any noise. You have to make sure any variation in analog signal is properly picked up. So the amplification is required. The initial value has to be maintained. So we want what is called a low noise amplifier. It is difficult to design. Of course, it's possible to design. There is nothing impossible. So the difficulty of designing the circuit makes the digital comfortable. Another reason is to reproduce, as I said, from a capacitor or any storage medium in analog, we are not sure whether what we got is what we stored. In digital, it is more or less accurate. Occasionally, a bit changes. So if you are going to reproduce 20 was stored, and if you recall it, it becomes 20 again 100. Very, very rarely one of the bits change and become 1011 or 101. That is very low probability. That is why we have enough accuracy. More than that, if you want to improve the accuracy or frequency range of an analog circuit, it's a lot of work, because it is not that simply you can extend anything. If you want to, you cannot make an amplifier with a gain of, let us say, 80. Then amplifier with a gain of 120. Not simply you change the resistors. What is the other problem? Unless it is an op-amp. Op-amp has, because of the properties of op-amp, it is easy. But generally when you build a transistor amplifier, it is very difficult to change the values. Redesign has to be done, especially in low noise pickup amplifiers. Whereas a digital, if I want to improve the accuracy, I add one more bit. The designing of the individual stages of a digital system are identical. If I have Let us say you have a counter. It counts from 0 to 255, 8 bits. 0 to 255 is 256. When you say 8 bits, there are 256 values. I already told you, either you can have 0 and 255 or you can have 1 and 256. But generally we start with 0 in digital system. So it is 0 to 255. Suppose I want to convert to 10-bit counter. Instead of 8-bit, 10-bit means 1024 levels. So it is 0 to 1023. Now I have to divide it into 123. So I need to add 2 more bits. So a bit is represented by a flip-flop. We will see it later. And I need to add 2 more bit flip-flops. That's all. So it's identical design. Not very difficult to design an extra range in a digital system. That is also the reason why it is popular. So today, most of the electronic gadgets, it works with digital systems. Because of the easy availability, people master digital design much easier than analog design, and the components, we can buy more of the same component. Whereas if you want to increase the accuracy of an analog signal, you may have to go for a different component. Low noise amplifier is not the same as normal amplifier. Like that. Noise suppression is very important. So that is the reason digital becomes popular and easy. But we cannot do away with analog. Don't mistake me. Because all signals in nature are analog. Whether it is sound bytes I am sending, whether it is video signals you are seeing, or whether it is whatever, all the senses, speech, hearing, touch, whatever signal you can think of, they are all analog. Naturally it occurs as analog. And first thing is to convert it into digital. So that is why we have 2 devices called analog to digital converter. And digital to analog converter. For short, it is called ADC, it is called DAC. Because I said all signals are occurring in nature and analog, they have to be first converted to digital before it can be fed into a computer. That is what I said, accuracy has been determined by number of bits, time interval you can define, all that you can do, but then the signal has to be digital, it has to go through this analog digital process. Similarly, once you do it, take the signal into the computer or whatever digital store material you are having, storage material, even just storing and retrieving. Even if you store something and retrieve it, that's a process. Not necessarily you have to do some huge complex processing. Or a DSP, filters. You want to do a filter, DSP define a digital filter. A filter has an algorithm. You write the algorithm, the filter works, but it needs input, you get output. So that is ADC. Once the process is over, because as I said it came from a real world source, most of the time we want to, for example, you want to hear. Microphone is there. Let us say it is a very noisy environment, a railway station. You want to reduce the noise in the signal. I put a microphone, I get the sound, but the sound if I send it to you, it is not cannot hear it. Already it is low signal amplitude. On the top of it, some noise would have added. So I have to convert it into some digital signal, do some processing, and then I have to send it back as loudspeaker, and that has to be analog again. So A to D converter, analog to digital converter, and digital to analog converter DAC are required analog systems. So let me summarize now whatever I have said so far. We go for, there are three types of signals. Analog signal, which varies between two amplitudes, and time is at any instant of time, any of the amplitude can be taken without any definition, without any limitation, of course within the range defined. Or the next is discretized time, discrete time. Time is discretized so that I don't have to take it every minute, every second, every nanosecond, because I don't know what interval of time is needed. So I discretize based on the frequency variation, how frequently the signal varies. Because any signal which is discretized properly with a frequency which is more than twice the maximum frequency of the signal can be reproduced accurately. That is the sampling theorem. So I have to define that discrete time signal, and then finally digital signal, where not only it is discretized in time, it's also discretized in amplitude, so that whatever amplitude is there is divided equally, and in between only the variation is allowed. So we cannot have every value possible from 0 volts to 5 volts. We would define this only 0 volts, 1.25 volts, 2.5 volts, 8 levels, like that. So, but analog signals are also important, because that is naturally occurring, and that is what most of the natural systems produce. So analog signals have to be also studied. Analog signal processing is not to be neglected. But digital became popular quickly because of easiness of algorithms, because with a computer you know how to work with a computer just by writing a program, and it's also easy to increase the accuracy. Generally the value that is stored in a digital system does not change unless there is a drastic, suppose there is a surge, power surge, the value will change. A huge amplitude is superposed on it, but generally not. But the analog signal can vary, even if it is mildly varying, we don't know how much. You store a signal in a capacitor, how leaky is the capacitor, we don't know. Even if you know how leaky it is, how long has it been there in that capacitor, we don't know that. So that is the reason analog digital signal processing is easier. So as I said, 90 to 95% of today electronic design is for digital design. Digital design is very popular because it is easy to master, easy to do devices, and easy to improve the accuracy, or anything you want to do is all out to add stages. It is like a 3-stage amplifier, getting into 4-stage amplifier is not easy. Whereas when I have 3 flip-flops counting from 0 to 7, I can have 4 flip-flops counting from 0 to 15 just by adding one more flip-flop. Whereas when I add an amplifier in the analog signal, it is not easy, I have to match it properly. It should not reduce the value drastically. Yeah, anytime you cascade something, there's a value fall. You know that. We have seen that multi-stage amplifiers. So there will be loss of amplitude, loss of gain, and feedback will result in increase or in input resistance, output resistance, increase input resistance, reduce output resistance, depending on the type of feedback. So all that has to be taken into account, and you have to match the loudspeaker, the microphone, to the input of the amplifier, and match the output of the signal amplifier to the speaker. So matching is also required. So all these are problems. That is why digital popular. but it is not to be neglected. That is what I want to emphasize again and again. Don't go about telling we don't have to know analog, we have to know analog. Without that, you are not an electronic engineer. Anyway, as I said, this is not my area. I am going to teach only digital, but I just wanted to say that. And we will now take into account what are the things we want to learn. That is why I have divided into units. Which unit I will cover when? For example, today I am supposed to be covering lectures 1 and 2 of NPTEL. Since you are not told in advance, of course it is there in the website which announced this course, the course content which is closely related to NPTEL lectures I have given earlier. So lectures 1 and 2, the introduction to digital systems. So tomorrow today also we have time. We will talk about that. And then I am going to introduce, sometimes I have to introduce new material because I want to improve the lecture content. Also, they may be important. So I will do that. You will see that in the course description again whenever new material is. So first two lectures. First lecture is lectures 1 and 2 or the first country. Yeah. This is the summary of NPTEL lectures 1 and 2. That is introduction to digital circuits, analog, discrete time and digital signals, advantage and disadvantage of digital signal over analog circuits. New material. Next two lectures will be new material, representation of numbers in binary, octal, decimal. This also most of you will be familiar with. Ones and twos complement and how to subtract using twos complement. And then we have lot of assignments and problems. I will send you the problems early to your mentors and they will have to monitor you are doing it properly and correct it because you can't get the things back here for so many people. And then, as I said, these assignments and problems are very important to understand the basics properly. So we will only talk about 2 weeks now. These two lectures, one lecture, two new materials and assignment. What is going to happen is, this program is formed like this. You talk about the lectures, you first come prepared after seeing these. After seeing these NPTEL lectures I ask you to do, please come prepared. I would like you to actually, I will just summarize it. In fact, today I am supposed to summarize, but I am going in detail because this is the first time and you may not be familiar with these lectures. So next time onwards, when I say do this and come, you are supposed to have read it and come or watched it and come and note down all the points you have, all the doubts you have, all the questions you have. We will have a discussion. So I will just briefly summarize what is going to happen and leave the floor open. I don't know, today audio is not working. I hope it will be solved by next lecture, which is Wednesday. So that you should ask me questions and I will answer them. That is the understanding of the thing. So every time there is a discussion, when I say the lecture content is this, you see, for example, every lecture I have put 2 lectures or 3 lectures for NPTEL in 1.5 hours here. Each lecture in NPTEL is about 50 minutes. So if we put 3 lectures of 50 minutes into one lecture here, I can only summarize what is happening. Then you have to come prepared, only then you will understand it. Then there will be discussion and problem session where you should, don't expect me to talk and you all keep quiet, then there is no point in this course. You are supposed to come up with questions. If you have a problem, you can also see the problems and come up with questions, doubts, so that I can clarify them. That is the format of this course. You can see this in the NPTEL. You go to the NPTEL website, IIT Madras, there is a flashing online course. You click that, courses will be displayed. Mine is digital, so click that, then you have the program there completely. The type of lectures, how many lectures, and then other things, so many things. And books, there are so many books on digital, there is nothing very, all of you know Mano, I hope, Morris Mano. Then there's a Roth, Charles Roth. Then there is this Tossi, Tocci. There are so many books. Wackerly, you can read one of them. It is not necessary to all read. Most of these people have common things. But occasionally one book will have something which is not there in other books. So you can have collectively together in one college. I don't know whether it is college or the library or you personally, you possess one set of these books and then you can always refer to them. When you solve the problems, you may require that. You can listen, of course, you'll understanding, but the problem solving is very important, especially for aiming to use these lectures for gate preparation or whatever. Today, gate preparation is important for not only postgraduate admission, even public sector units want to recruit based on gate scores. So gate is become an important exam, and these things many people have written to me earlier that they have seen my NPTEL lectures have been of great use for them in gate and job interviews and so many other things. So I want you to get the same benefit. Okay, that is what it is. So, what is the main performance measure? You see, when you have a circuit, analog circuit will usually say noise and of course bandwidth and frequency response. These are generally the performance measure in analog circuit. In digital, what are the things? Digital, as I said, everything is reproducible. I can reproduce anything that I put there. In memory, if I store something, I can get it back. You have this experience from your cell phones. You store, you save all your contacts, and then you can recall them. There is no corruption. So that is one thing, but we will not talk about it. We have already told you about that. That is why advantage of digital systems over analog. But what is because so many things are happening in digital, this 5 volts, 0 to 5 volts is the sort of a general numbers. Today we have low voltage supply circuits. They work with 0 to 3.3, they even work with 0 to 1.2, and they are going to have sub 1 voltage, 0 to 0.8 and all that. And there, of course, there will be noise, because once you have a small range, the range with which you have to define your thing, if it exceeds, there will be noise. What is the noise in digital system? The noise in a digital system is when this value is different from what you have. For example, if I have 0 to 5 volts as my signals, and if it is, I try to make anything above certain voltage like 3 volts, 1, any voltage less than 0.8 volts, 0. So 0, 5 volts is ideal. You don't have to have that. I can have up to 0.8 volts low and up to about 3 volts as high. 3 to 5 high and 0 to 0.8, 0.8 to 0 is low. So if I have a signal which is low, 0 volt, I put it as a 0 signal or 0 value. When I measure it, became 1, it has exceeded the limit of this 0.8 variation and got into the mid-range, which is undefined, or it can even go into the higher level of, then it is a signal. 0 will be read as a 1, or 1 will be read as a 0, that is a noise. But it's, as I said, it is very, very rare. There is how we define noise margin, maybe we will see about it later. But what are the other important parameters today? Today, as I said, lots and lots of digital circuits are packed in a single IC. Very small ICs, you might have seen, all of you might have seen microprocessors. Cell phone you open, circuit is so small. And every system today is very compact. Many of you have the small micro type of things. That is, size is one important factor. How much can you reduce it? Then, how far can you go? That is speed, because that is, for example, when you use a computer or a DSP, let us say computer, you want to store some information or retrieve some information. You want to have it instantaneously. You have a JPEG image coming into your computer, you want to see that, you do the double click, and you have no patience if it takes a lot of time to come. You want it immediately. It depends on the speed at which it works. Same thing with cell phone. Any digital system or any system for that matter, how fast can it respond to change? That is one important issue. Then power dissipation, that is very important too, because as I said, power is at a premium. For two reasons. One is, usually these are portable devices. So a cell phone, there's a battery to be charged, of course depending on the use. Some people have to charge it every day, some people can wait for 2-3 days or 4 days. Same thing with laptops. There's a battery, you charge it and start working, after some time it goes battery slowly. Again, depends on the speed and the type of operation you do. So speed, the power dissipation. So the power should be reduced. So low power design is very important today. Low power design, circuits which consume low power. And then this is another second reason why it is important is, as I said, you are packing a whole lot of digital circuits in a single IC. In a single IC, you have so much design, so many circuits, and then they are so close to each other, it generates a lot of heat. And this lot of heat you generate will stop the circuit from working after some time. It will damage the circuit also, so you have to cool it down. So you want to make it low power dissipation so that it doesn't affect the other circuits nearby. It is one thing. Okay? And then of course cost. You want to buy the most, you want to buy a more sophisticated cell phone, iPhone 5, you want to buy, or you want to buy Nokia, what is that, Luma, I don't know, there are so many brands. Calculator, the calculators have so many features today, programmable calculators. You want it small, so that you can put it in your pocket. You want the power should be low because you don't have to charge the battery every time. And size, as I told you, speed, I told you, speed, it should work fast. Power display, I told you, and you want to have it as cheap as possible. You don't want to spend a lot of money. You want best possible thing. Digital TV today, everybody talks of digital TV, multi-channels, split screen, so many features you want to have in a digital TV, but you do not want to pay a lot of money. So cost. So these are 4 parameters by which you measure the performance of digital system. We may not add but once you have a design philosophy for speed and power dissipation, you can extend it to any big circuit. You don't have to teach a microprocessor to start with, because microprocessor is made up of a central processing unit, input unit, output unit, memory, program memory, data memory. The computer is made of so many input devices, keyboard, you write a pen, using a pen you write the input. Output can be digital, it can come in the LCD, LED, or it can come as a monitor. So whatever is the thing we want is all these 4 parameters. You have to keep these in mind. any digital this system you are going to design in future, because this is one simple way of learning digital. Because digital is one thing, if you learn the basics, you can always expand it. When you go to the workplace, wherever you go, you will use your basic concepts and build a bigger circuit. So when you build a bigger and bigger circuit, especially in for a company, they will expect you to do it at very low cost. They want to make it a very small size, speed, and they want to have as low power dissipation as possible. So these are principles that are to be borne in mind, even though we will not be using all these to start with. We will be starting with simple circuits. Okay. So now that we have talked about all this, let us have a quick look at how a digital system looks like. So this is the digital processing. It can be a computer, it can be simple. I will call it digital processor. It can be a computer, or it can be a DSP, or it can be a simple circuit which can do even accounting is a digital processing. So you put anything which counts, you put input as numbers and output as numbers, that is a digital process. But then, as I said, we have analog signals. So I need to have, let us say, the real world signals are analog. What do you mean by real world? That is all this real world. I have to digitize it using a digital to analog converter, but it's not simple. You cannot just put the DAC. So you have to first remove noise in this, band limiting. Because you want to remove circuit filter, band limiting filter. Because there may be frequencies which are beyond the capability of this. There may be signals, there may be noise. We want only, for example, you want to amplify a low frequency signal. There may be some spikes, high frequency there. We don't want them to be amplified. So we want to remove them. That is called band limiting. I limit the bandwidth of this signal, original signal. It's called band limiting. Then I have to do a DAC, digital to analog to digital converter, ADC. But before that I have to do sample and hold. Because sampling is a discretizing process. What is the hold? As I said, this takes some time for the ADC to work. I discretize it, the signal. Let us say I have done it with a digital signal. Time, amplitude. Digital signal. So I want to, this analog signal, I want to sample at this interval and then this interval, maybe it's a wrong representation because the trick varies so fast. I have to maybe do it more frequently, that is okay, it's only the concept. So this value, once you give this value, it will not be immediately converted to analog, digital signal. It will take some time. So I have to hold this signal at this value till the process of A to D conversion is over. So this is required. So this is called sampling That is, at whatever instance of time you want to find this value is called sampling. Sampling is whatever instance you want to get the value signal, and hold is to keep it for a while so that ADC can, analog digital converter, can work properly. Then you go to the ADC. I'm not showing the details because nowadays they have ADC which is, you require buffer. This is these are single signal. Analog signals are single signal, whereas digital signals are multiple levels. So this becomes a multiple level signal. I put on this bar means it is multiple levels. Multiple, I have to feed that. And then I do the digital signal process. Then I get the output using a DAC. And I have to represent it as an analog signal. So I start with an analog real world, convert it to digital by an ADC process. Before that I have to do some pre-process, it's called pre-processing. I have to limit the bandwidth, I have to sample it and hold it, then ADC, and then do the digital signal processor. DAC will give you values in discrete intervals, but that is not enough. I want a continuous wave of the output, so I pass it through a filter, will smooth out, a smoothing filter, and then it gives you the analog value which I use in our analog system in the world. That is how it works. So this is the sample, but we are interested in this. But digital processor need not be a big computer, need not be a DSP, need not be a microprocessor. A simple set of gates and flip-flops, memory is a digital processor. We will see that later on in this course. That's all today. I am going to stop here. And